This video is about Kepler's laws of orbital motion. Johannes Kepler, a German astronomer, developed his 3 laws of orbital motion in the early 17th century. We'll begin by stating these 3 laws, and then move on to discuss each law in a bit more detail. Kepler's first law states that planets move in elliptical orbits with the Sun at one of the foci. According to his second law, the line that connects a planet and the Sun sweeps out equal areas in equal times. Finally, his third law says that the square of a planet's orbital period is proportional to the cube of the semi-major axis of its orbit. We'll now explore each law in a bit more detail. The first law states that planets move in elliptical orbits. The 2 focus points of this ellipse are here and here. We can add the planet, for example, here. Now don't worry much about what the focus points or foci represent geometrically, just be aware that according to the first law, the Sun is at one of these foci, so for example here. Moving on to the second law, let's compare what happens when the planet moves between these 2 points and between these 2 points. We'll add the lines connecting the Sun and these points, and now analyze what the second law says. If we denote the time it takes for the planet to travel between the first 2 points as t1 and the area swept out by the lines as a1, while denoting the travel time of the planet between the other 2 points as t2 and the area swept out as a2, then according to the second law, we can conclude that t1 is equal to t2 and that a1 is equal to a2. As these times are the same, we can also deduce that between the first 2 points we drew, the planet is moving slower, since here it travels a shorter distance compared to this length, where it is moving faster. In order to discuss the third law, we'll add the semi-major axis to the diagram, which connects the center of the ellipse to its perimeter, passing through one of the foci. We'll denote the length of the semi-major axis as a. If we then denote the orbital period of the planet using the letter uppercase T, then we can write that t squared is proportional to a cubed. We can express this relationship more precisely using the formula t squared is equal to 4 pi squared a cubed divided by gm, where g is the gravitational constant and m is the mass of the Sun. Now for a circular orbit with radius r, the formula becomes t squared equals to 4 pi squared r cubed over gm, which is exactly the equation that we discovered when we learned about Newton's law of gravitation and the link between gravity and orbits. Little surprise that Newton was inspired by Kepler's discoveries and that some of his work is based on Kepler's insights. With this we have completed our video about Kepler's laws of orbital motion.